The fifth and final example of a statistical application is the U.S. House of Representatives turnover percentage. And as you can see in the table below, here are the various decades, the 1870s through the 1980s. And in each one of those decades, this gives you the mean turnover percentage. Since there are elections every 2 years for members of the U.S. House of Representatives, each one of these values will be the average of 5 turnover percentages for that particular decade. So these numbers have a little bit more stability than one single election. If you look at those mean turnover percentages, you can see that they are going down. At least it looks that way superficially. We'll see that in a minute in a plot. And what you can conclude is that back in the 1870s, maybe two things. Life expectancy was shorter. So that's certainly going to be the case. The other thing you can probably assume is it was more likely that somebody would get elected to the U.S. House of Representatives, go and serve a term, maybe 2 terms, and then they'd come back and take the job that they had prior to leaving for Washington. Whereas nowadays there are more people that will become career politicians. Now, on the next slide, one thing you could do with this particular data set is fit a simple linear regression model. So that's y, which is going to be known as the dependent variable, will be some intercept a plus b, which will be the slope of the intercept line, times our dependent variable x plus some random error term epsilon. Sometimes it is of interest when you're doing simple linear regression to test, and this is known as a null hypothesis H0, that the turnover percentage has a slope of 0 when measured against time, and that's known as a null hypothesis. And in this particular case, we might be interested in saying, is there statistical evidence that the turnover percentage is decreasing? And this is known as an alternative hypothesis. And that is H1, is that that slope is negative. Now, if you go to the next page, there is some R code. And this R code has produced the plot that you see up above here. So first of all, I take each decade from the 1870s forward, and there are 12 decades, and I just assign those the integers 1 through 12. Second thing I do is I use again the combine function, which you saw earlier, to create a vector known as turnover. So again, decade will be the vector 1 through 12. Turnover will be the vector 50.3 in the first position all the way up to 12.9 in the 12th position. Then when I call the R plot function, with decade along the x-axis and turnover along the y-axis, I get these dots. So what this produces here is this will plot the points only. I might be interested in not only the points, but what is known as a regression line. And that regression line can be calculated and plotted with the next 2 commands. First of all, I set reg to the results of calling lsfit, and that stands for least squares fit. There is another routine that I could have called here called GLM, which stands for general linear model. But in any case, I put in decade and I put in turnover, and when I do that, I am fitting a regression, and then I can call AB line with the coef for coefficient part of regression, and it will give me the slope and intercept, and it will actually plot that line right there. It's pretty clear in this particular case that there is a decrease in the turnover percentage over time, and that null hypothesis that we had stated earlier would be rejected. So this is the end of the statistical applications, and now we move on to section 1.2, which is counting.